All right, welcome to chapter 6. This is a pretty easy chapter, especially coming off of chapter 5, which has some crazy stuff in there. Chapter 6 is all about periodic trends and the periodic table. All right, so let's first kind of talk about the development of the periodic table. So back 1800s, Russian scientist Dmitry Mendeleev, he's given credit for developing the periodic table that we use today. There's lots of different types of tables, but this is kind of like still the main one we use. It's an awesome design, and I'll tell you a little story about how he actually wasn't the only person to come up with this same idea at the same exact time. But what he did is he took a bunch of the elements that they knew at the time. They knew the masses of a bunch of these different elements, and so he just kind of laid them all out on a table in front of him from light to heavy and was looking for patterns. And they see that every 8 or so elements, the pattern will repeat, right? In fact, for the lighter elements, it is exactly every 8 elements, and they used to call it the law of octaves. But for example, lithium, it's a soft gray metal. You can cut it with a butter knife. Sodium, soft gray metal, cut it with a butter knife. Potassium, soft gray metal, cut it with a butter knife. If I take lithium and I put it into water, it sputters around. It releases a bunch of hydrogen gas, right? If I had a phenolphthalein, which is an acid-base indicator, it would turn nice pink color here. I can do the same thing with sodium. Sodium also reacts with water, produces a bunch of hydrogen gas, and it would also turn it pink if that indicator was in there. Potassium, same thing. Fire, flames, all right, a little more reactivity looking like on here, but it's also producing hydrogen gas, and it would turn the stuff pink when it's all done. So this pattern repeats, all right? And the reason that the periodic table is called the periodic table is because the physical and chemical properties repeated periodically. All right, so that's kind of cool. If we look at these things, so if I go from like lithium all the way over to neon, there's a certain pattern in the reactivity. And then when I go sodium all the way to argon, it's actually an extremely similar pattern in the reactivity. So when I lay it out like this, what happens is that all these groups, these columns, end up having elements that all react very similarly. So if you look at all the different oxides these things form, and you see there's a pattern, all right? So that's kind of the whole gist of this thing. So the other guy who came up with this idea was Lothar Meyer. All right, so Lothar Meyer, most people haven't heard of. Mendeleev, most people do hear of, and I'm going to show you why. Because Mendeleev did something really cool. When he made his periodic table, he left gaps in it, like holes. And these were places where he predicted there would be something, but it was something we hadn't actually discovered yet. So he left these gaps in the table for undiscovered elements, which is pretty cool. But way cooler than that is he made a bunch of predictions on like the physical and chemical properties of these elements. So for example, like right under silicon, there's this gap in his table, and he called it ecosilicon, just means after silicon. Later on, much later on, the element that goes there is what we call germanium. But he made these predictions back in 1871, and the element wasn't discovered until 1886. So 15 years prior to its discovery, he predicted the weight, the density, the specific heat, melting point, color, like all this stuff. And if you kind of compare to the actual experimental stuff, you'd see it's insanely close. So that's why Mendeleev is, pretty darn famous. And he did this for 2 other elements, and I can't remember which ones they were. But yeah, so it was like 3 elements where he did this, and his predictions were really spot on. Very cool. So the table was really cool. Everything was good, but there's a couple things that didn't quite work. There's just a few things that weren't fitting in. They had some things that were in columns that they weren't acting like the other things. And the reason is putting all of the elements by increasing mass wasn't quite right. A guy named Henry Moseley had the idea, let's put it by atomic numbers. So that actually doesn't change hardly anything. The order stays the same for these things, because as the atomic number increases, the mass increases, right? But there were a few instances where it switches around. So if you look around like cobalt and nickel, like get your actual periodic table where you can read these, because these are too small to see, but you'll see like, ooh, that's different there than tellurium and iodine. Look at the masses and then look at the numbers. You'll see where those would be flipped in Mendeleev's table. So the periodic law says the physical and chemical properties of the elements are functions of their atomic numbers, and our modern periodic tables are arranged in order of increasing atomic number. All right, swell. Let's do another couple little things here. Let's pick some elements and then figure out the valence electrons. So you guys know how to do configurations now. So let's do oxygen, sulfur, selenium. So if you're going to do oxygen, it'd be 1s2, 2s2, 2p4. All right, and then let's see, sulfur should be 1s2, 2s2, 2p6, 3s2, 3p4. And what the heck? Let's click back here. And let's do selenium too. Why not? So if I'm going to do selenium, get the electron configuration, that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. So the valence electrons on selenium are just that, the ones with the highest principal quantum number. So it's not the 3ds, it's the 4s and the 4p's. So I had 2 there and I had 4 here. So that's 6 total valence electrons. When I go back to sulfur, right, its highest shell was the third one. So 3s2, 3p4. 2 plus 4 is 6. So this has 6 valence electrons. Same thing here with the oxygen. All right, 6 valence electrons. This explains why these things are acting alike. Right? They have the same outside electron configuration, so the valence electrons are the same, so they react the same. Pretty cool. All right, what else we got going? All right, yeah, so the electrons in the outermost principal quantum level atom are the valence electrons. Yepper. So when you're looking at a configuration, like 1s2, 2s2, 2p6, all right, it's the electrons that are in the highest principal quantum number, those shells. So the highest energy shell. So in this example, right, these 2 electrons that are in the 2s and the 6 electrons that are in the 2p, those would be the valence. So there would be 8 valence electrons on here. And elements in the same group of the periodic table have the same valence electron configuration. I just showed you that. Pretty cool. So there's another trick. I'll explain to you a little bit. I'll do just the quick version. Basically, the group number, right, will equal the valence electron. So group 1, all those elements have 1 valence electron. Group 2, those have 2 valence electrons. Group 13 has 3 valence electrons, so there's kind of a jump as you cross over that D block there. But group 14 has 4 valence electrons, group 15 has 5, group 16 has 6, and so on. So that's a cool little trick that we can use to get the valence electrons. All right, I will catch you guys in the next video. See you then.